Alright, so Cfat number 2, we're looking at 9E to 9H. Given this following graph, write the number of faces and edges. Yeah, this is easy. So remember, faces refers to basically these little spaces here. So you've got 1, 2, and the outside counts as a face as well. So faces equals 3. The number of edges is going to be 1, 2, 3, 4, 5, 6. Okay, it's easy. Given the following graph, next one, find the number of faces and edges and vertices found in this graph. So the tricky thing with this graph is not planar. So you have to make it planar before you actually do this, because what some kids will do is they'll just look at it and say, oh yeah, this has 1, 2, 3, 4, 5, 6, 7, 8, 9. Incorrect, okay? It says here there should be 6 faces. So that doesn't make sense. So make this planar first, all right? Always start by making it planar. Do your vertices. Try to keep them in the same spots if you can. Just makes it a lot easier for you, okay? And in this case, I have how many edges? So, there's a couple things that I need to move here. Here, the lines are intersecting. Okay, so, actually, I'll leave that one there. Yeah, I'll leave that. But I have this connection, this connection, this connection. I also got this connection here, that one, and that one, and that one. Okay, and I will keep this connection. So the only connections I haven't drawn is this one and this one here. Okay, so I need to redraw them to make it planar. So I can see I can actually put this one here, make it go around. That's one, and then the other connection I can just go here. 2. Okay. All right, now counting the number of faces for this graph. Let's go. So you've got, we're looking at faces, vertices, and edges. 2. Just going to double check I drew the right ones. Oh no, I drew the wrong one. Sorry. Let me fix this up. I drew this one. Okay, but I didn't draw this one. So this graph, sorry, should be connected there. That's better. So paste to double check what you've drawn and what you haven't drawn, just so you know what's going on. Okay. All right, let's do this. So I've got 1, 2, 3, 4, 5, 6, 7. Okay, I think this might be incorrect then. Yeah, it's probably wrong. This should be 7. I think people would have had 7 as well. All right, so in that case, 7. The number of edges I can see are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ooh, okay, why is this? I think the person didn't do this properly. There should be 10. And then the number of vertices, I can see there's 1, 2, 3, 4, 5, 6. Okay, so I'm going to fix this. So faces, I think it was 7. The edges was 10. And the vertices was 6. All right, next one. Oh, okay, I already redrew it as planar. Question 4, the graph below shows the pathways linking 4 sites. List a trail found in this graph. Now, this is those, I think, 5 words that we learned before. Trail, path, circuit, cycle, and there was another one. Can't remember it. Trail, path, circuit, and walk, sorry. But walk sort of is like a free for all, you can go anywhere. All right, remember a trail, okay, just means no repeated edges. Okay, so you can actually go anywhere, you just can't repeat an edge, okay? You can have multiple answers for this, given that it's just a trail. Technically, you can just go N to M. There's a trail, okay? I didn't repeat any edges, okay? You can go N to M to L, and then back to K. There's another trail. Okay, the idea is you just don't repeat any edge. Or if you want, you could go N to M to L to K, back to N, and then up to L. And I've gone through every edge once. The main thing is no repeated edges. And you can repeat a vertex if you want for the trail. So there's multiple answers for it. The main thing, again, just you don't repeat an edge. Alright, you can list a circuit. So a circuit just means no repeated vertices, which means you can't go back to the same vertex twice unless it's the start and finish. So if I want, I can go N to M to L, K, and then back to N. That's a circuit, sorry. That would be considered a circuit. Now, in this scenario though, for it to be a, oh, sorry, I got that confused with the cycle. A circuit just means start and finish have to be the same, okay? But you can't repeat a edge. So in this case, okay, there is a circuit. Okay, so N, M, L, K. Sorry if that confused anybody. A cycle would mean you'd have to go all through every vertex just once, but a circuit is every edge once. Start and finish is the same. So that's one of them. You could also go N, M, L back to N. That's another one. Just make sure the start and finish is the same. You could even go K, L, N, and then back to K. Okay, that's also a circuit. All right, let's go. Is the graph traversable? Okay, so traversable, this just means go through every edge once. That's what traversable means. Okay, can you go through every single edge once? Is this a yes or a no? Well, it is a yes, because if you look, at least two of the vertices are odd. Now, when we get to this territory, remember, if it's traversable, that's when we get to the Eulerian trail, yeah? So if you look at this, two of the vertices are odd. So I would write as an answer, yes, it has exactly two vertices that are odd. And that means it's a Eulerian trail of some sort. All right, for that question. And if you wanted to find it, remember, you just find the ones. Okay, just find the vertices that are odd, and that's going to be your start and finish. So if I start here, remember, you're trying to cross every single edge once. There, I finish here. If I start at L, okay, I have to finish at N here. So the start and finish for a traversable graph with two odd degrees is going to be the vertices that are odd. All right, let's see. Next one. Oh, I should write an answer. Yes. Okay. This question, a connected planar graph has 7 vertices and 10 edges. Find the number of faces in this graph. So this is where you use Euler's formula. V plus F equals E plus 2. So in this case, you've got 7 vertices, 10 edges. How many faces? Okay. So you've got 7 plus F equals 10 plus 2. In this case, you're going to isolate F. So working out the formula, 7 plus F equals 12. Isolate that F, so that means you get rid of that 7. It's a plus 7, so here it becomes minus 7. So 12 minus 7 is 5. The answer is 5 faces. Find the sum of the degrees for the vertices of this graph. Okay, so in this case, one way you could do it is you could technically you could just draw the graph, because you have enough information here now. Yeah, you've got 7 vertices, 10 edges, and 5 faces. So sometimes you'll be asked to do this. Yeah, 7 vertices, 3, 4, 5, 6. Let's go 7. And here you've got 10 edges, so you have 10 edges to work with, and you have to have 5 faces. Let's see if we can do this. So again, I've seen this question in a Cfat or the SAC before. So you've got 1, 2, 5, 6, 7. So I've got 1, 2, 3, 8, 9. I've got 1, 2, 3, 4, 5. I can only have 5 faces, yeah? So I think I've already gotten too many. Let's see, if I drew, so remember I can only have, the rules here, 7 vertices, 10 edges, 5 faces. So I've got 1, 2, 3, 4, 5, 6, 7, 8 edges so far. There's 9 edges, so I've got 1, 2, 3, 4 faces. Good, I'm nearly there. And if I drew one more here, I'll have 5 faces, yeah? So, and then how many edges? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's correct now. And I've still got the correct number of vertices. Did I have a question there? Okay. No question. All right, so there's my graph, and then from there you can figure out. Oh, sorry, Joseph, did you have a question? You can figure out the number of the weight of this graph. All good. You can figure out, sorry, the degree of this. So the sum of the degree. So you've got the degrees here. If you want, you could write down the degrees for each vertex. So here you've got 2. Here you've got 3. Here you've got 3 as well. 3, 2, 2, and that's 1, 2, 3, 4, 5. And then you just add all the numbers up. So 2 plus 3 plus 3 plus 3 plus 2 plus 2, and then plus 5. And it should equal, if we did it correctly, should equal 20. So adding them all up, that's 7. Oh, that's that. 5, 8, 11 plus 2 is 13 plus 2 is 15 plus 5 is 20. So we did it right. Alright, next part. Find the number of odd degree vertices this graph will have. So, because I've drawn the graph already, how many odd degrees are there? 1, 2, 3, 4. Okay, so there's going to be 4. Okay, last 2. In the area of the town Zenith, a postal worker delivers mail to 10 houses labeled as vertices A to J in the graph below. For this graph, a Eulerian trail does not currently exist. Okay, so this is saying that you can't go through each edge once. Currently, okay, you can't go through all the edges once. For a Eulerian trail to exist, what's the minimum number of extra edges that the graph would require? Alright, so again, some of you guys got confused about this. What I would do first here is I would first identify how many odd vertices I have and label them. So for example, E has 3. So I would write that here, right next to it. G has 3. A has 3. D has 5. Okay, B has 3. And that's it. Okay, so the question here is how many odd vertices, how many lines do I need to add, or edges do I have to add here to make sure that a Eulerian trail will exist? So remember, for a Eulerian trail to work, I missed one here, sorry. You got to make sure that you have 2 vertices that are odd. Okay, at most only 2. So if I was to add some lines here or some edges, I could add 1 from E to A. Now this will make them even, okay? But I still got 1, 2, 3, 4 vertices that are odd. So that's 1 line I've added. So I can add another line. So I might add 1 between I to G. And that will make them both even. So now I've got 2 vertices that are odd, which means that a Eulerian trail will exist here. So how many edges do you need to add? 2 extra edges. And now you can add them anywhere, okay? It doesn't have to be where I've added them, okay? So for example, if that was 3, 3, 3, and 3. I could have added it between D and G. That will make them even. And I could have done it between B and A. That'll make them even. Okay. But the idea is, it's just asking how many edges do you have to add to make this a Eulerian trail, which means having 2 vertices that are odd. All right. Next question. Same question. All right. But Eulerian trail doesn't exist. However, the question is this time, a Hamiltonian path for the postal worker starting at F would be Hamiltonian path. Okay. Remember, Hamiltonian just means go through every vertex. Okay, that's what Hamiltonian means. Now, because it's a path, you don't have to start and finish at the same spot. But the question does say you have to start at F and you can finish anywhere. All right, so we're looking for a Hamiltonian path where you go through every single vertex just once. Not every single edge, every single vertex, just once, but you have to start at F. So if I start at F, I can literally go anywhere I want. So I can just go, for example, F, E, H, I, J, and G, D, C, B, A. Okay, and then remember the start and finish doesn't have to be the same, but you just have to go through every single vertex once. That's one of the paths that you can take, yeah? You can actually take multiple paths for this question, as long as you start at F. I could have gone F, D, C, B, A, E, H, I, J, G. There's another one. I could have gone F, D, G, there, I, J, H, E, A, B, C. There's another one. This is why it makes it so easy in that sense, because you can just go anywhere, again, as long as you go through every single vertex and you start at F. Makes it a headache for me to mark though, because you all might have different answers. But in terms of listing your answer as well, you could just write it, for example, as, so let's say that's the path I took. F, I, also write it like this, yeah? So do the little dashes. J, G, oops. This will make it easier for me to mark, or what was I up to? D, C, B, A, E, and then H. Okay, remember, you don't have to start and finish at the same one for it to be a Hamiltonian path. If it's cycle, then start and finish has to be the same. All right, I think that'll be it for this.